And then we need to add our remote. So let's go ahead and do that. And then we'll git push u origin main. Okay, so you can see we handled that relatively quickly. If we refresh on GitHub, we should now see all of the code that we have just created. So with that set up, what I'm going to do is, as the series progresses, I'm going to put somewhere in the video here a current commit that we're on, or a previous commit that we've committed. That way you can keep track, if you are working with the repository, exactly what location in the code we're at in terms of time as we progress through the project. Okay, so let's head back into the solution now. What I'm going to do is just close all of the tabs, and the first service that we're going to work with is our precipitation service. So if we expand precipitation service here, we've already started work on sort of minimizing program.cs. What I want to do is just sort of demonstrate how we can map a new route using a minimal.NET 6 Web API. In fact, we can just call MapGet on our web application instance. As a first argument, we can provide the path. So think of this as the endpoint that we want .NET to listen on. In this case, let's say we have something like observation, and then let's say we want to take a dynamic value, like we want a user to provide their zip code. Well, we can do that with curly braces, and so we can say curly braces zip. And then as a second parameter here, we essentially provide a delegate. So this is sort of an anonymous function. And you can see we don't necessarily have to have that function execute any code, but the idea is that this is the function that will get executed when a route matching the first parameter is hit on our API. So if we want to pass that zip code dynamically, we just pass it as a parameter to this delegate. And let's just say, for simplicity, we just want to return a 200 response to a user that hits this route, and we want to echo back their zip code. We can return results.ok for the 200 there, and then pass zip as an argument to return that on the response. So just a bare bones sort of smoke test to get started here. Let's take a look. We can right click on cloudweather.precipitation, set as startup project, and then hit play. Now we set things up so that the browser is not going to open automatically, and that's fine. But let's keep an eye on the output window here in Visual Studio. So ultimately, after things build, we'll see that it's deployed, or rather running, on port 4000 on localhost. So let's open up a browser and see if we can hit port 4000 /observation /zip. Okay, so here we're just getting the string zip out, but we can provide a zip code here. I'm just going to make a random number up, and we can see that's echoed out. So what's happening here is .NET is just interpolating the value that we're providing on the request, in this case through our browser, and echoing that value back out to us in the HTTP response. And so we're just getting a simple string value back out here. So that's interesting. Of course, it's not very useful, but this is useful in the sense to sort of understand how we can, in this case, map a GET request to a particular endpoint. Let me go ahead and just stop things here. And so when we're talking about a precipitation service, what we want is the ability to return precipitation data to our user when they make a GET request. And we want to provide a zip code, or our users want to provide a zip code, and they also want to provide some time range. And so let's imagine that this service is responsible for returning some historical weather data for some number of days in the past. And so one way that we might want to handle this is via a query parameter on this route. And we can do that using the fromQuery attribute and say an integer value days. And we'll make this a nullable integer value and handle the null here. For this, we need to actually bring in Microsoft.ASP.NET Core.MVC to get this particular attribute. But now we can actually make use of that attribute when we're actually querying for data. So we'll look at that shortly. But let's think about this concept of querying for data. If we need to return some precipitation data, then clearly we need to be interacting with some data storage. And in this case, we're going to be interacting with a Postgres database. Now, one of the ways to interact with databases in .NET is through an ORM, or Object Relational Mapper. So an ORM is basically any type of software that really sits in between a software code application layer and the data layer. The ORM is really responsible for mapping types in the language, in this case C# classes, with types in a database. So think things like tables and rows in a database. And so EF Core, if you've watched the channel before, then you know I've used a lot of EF Core in these videos, and I've used it on many projects otherwise. And it's a very nice, easy to use ORM. It works in a code-first fashion, meaning that we can essentially define our database schema using C# classes, which is very convenient. It also enables us the ability to create what are called database migrations, so that if we make changes to our schema, we have a controlled way of rolling those changes both forward in time and backward in time as we're doing development. So we're going to set all of that up now. For this, we actually need to install some Nuget packages, and in fact, we're going to take care of installing all of our project dependencies now. So I'm going to right-click on Precipitation, and we're going to manage Nuget packages. First of all, we're going to remove Swashbuckle because we don't need to use Swagger at this point in time. And we're going to add, we're just going to search here under Browse, we're going to search for EF Core. And what we want to install is Microsoft Entity Framework Core. And we'll accept. We're also going to install Entity Framework Core.design and accept, and Entity Framework Core.tools, and we'll accept that. Next, we're going to install a package called npgsql, and specifically npgsql.entityframeworkcore.postgres. This is going to enable EF Core to work with our Postgres database. The other thing that I'm going to install here is extensions.options. I believe this is going to be necessary for using the options pattern, which is something that we'll look at a bit later. We're also going to be installing extensions.logging to install our logging infrastructure dependencies. Okay, so that's about all we need. A really easy way to actually sort of copy dependencies or define the dependencies that are needed across projects is to edit the CSproj file here. So if we right click and edit the project file, we'll now see an item group containing all of those dependencies. So let's go ahead and copy this. And we're going to copy them directly over to the CSproj file for weather report. Again, replacing swashbuckle as it's not needed. And then we'll do the same for temperature. Our console app won't have all of the same dependencies, so we'll leave that as it is for now. We'll go ahead and save all of these. We'll right click on the solution and make sure that it builds. And if it succeeds, which it does here, we'll go ahead and make our next commit. So we'll go ahead and git add all, git commit -m, add initial deps, and I'll go ahead and push. Okay, so we'll close all of our CSproj files here. And under Precipitation, what I'm going to do is I'm going to create a new solution directory, so a new folder here. We're going to call, not a solution directory, but a folder in this project actually, and we're going to call this data access. Now we're going to create two separate files in our data access layer. Things are going to be very simple for this microservice, which is a good thing. We're going to add a class here called Precipitation. So we'll grab class, and we're just going to call this Precipitation. Next, we're going to add another class called Precip DbContext. So Precip for Precipitation, DbContext. Now, if you haven't used Entity Framework before, or Entity Framework Core, the concept of a DbContext is basically an abstraction on a database. So we can think of a DbContext as representing a database, and what we'll see in a moment here is a generic type dbSet of a particular C# type represents a table for that type that Entity Framework will map for us. So we have this type Precipitation, and effectively we're going to create a dbSet for this type Precipitation in our DbContext, and EF is going to essentially map our Precipitation object to records within a precipitation table. And so we'll be able to query our database using Entity Framework, and it's going to serialize the data that it gets back into instances of our precipitation data model. So here's what this model is going to look like. It's pretty straightforward. We're going to have a GUID as a primary key. Its name is ID here, and EF is going to intelligently infer that this is the primary key relationship on that table. We're going to have a date time for created on, a decimal value for amount inches, and string types for weather type and zip code. So EF under the hood is going to be mapping these string types to varchars in SQL world, and the appropriate numeric type for decimal, the appropriate date type for date time, and likewise for the GUID. Okay, so now let's take a look at our DbContext. First of all, we need to extend DbContext here, which is coming from Microsoft at Entity Framework Core. Then we're going to create two constructors here, a parameterless constructor, as well as a constructor that takes an instance of a DbContext options object and passes that to the base class DbContext. And then we're going to create our dbSet of type precipitation. So as I mentioned, dbSet is a generic type. This is actually just going to be defined as a property on our dbSet, or our DbContext. And the only other thing I'm going to do in this particular class is override a method on DbContext called onModelCreating. This takes a model builder instance, and we can call onModelCreating on the base class, pass it the model builder, and then we can sort of override any sort of custom behavior we want here directly within the Precip DbContext class. And so what I like to do is snake case table names. So by default, EF would create a table in our SQL database called precipitation in Pascal case, just as we've defined here in a C# class. But I personally prefer to have snake case SQL table names. This makes things just a little bit more convenient for me in terms of querying the tables. I prefer snake case. For instance, with Pascal case, if we were going to query using raw SQL and we had a capital letter anywhere in here, we would need to in the SQL query put double quotes around the table name. We can avoid that just as a convenience by making the table names snake case in the first place. So I like to do that. Plus, this demonstrates an example of things that you can do when you override onModelCreating. So this is going to get called when Entity Framework Core actually creates this table in our SQL database for us. And so we can do anything that we have access to on this model builder, including define for any particular entity table names, among lots of other types of configuration we can do here. But for our case, this would be sufficient to snake case those table names. Okay, we don't have our database yet, but now conceptually we have a way to query for precipitation data. So since that's the case, I'm going to head back into program.cs, and we're going to think about exactly how we want to query our data when a user hits this particular endpoint. Well, one thing is we mentioned that we're going to query for some number of days, but we need to actually work with the database itself, and we can actually pass that here, precip DbContext, and we'll call this DB, and we'll bring in our data access namespace. Now, this is very convenient because we can just immediately start querying for data here. So let's say that we want to get all the precipitation records that match the past zip code that's on the path parameter and that are, say, some number of days in the past from the time of query from the database. So we can actually do this. What we can do is we can say something like var results are equal to db.precipitation, and then we can provide a where clause here. So we can say where, and we could say the precip dot zip code is equal to the zip that we pass on the path parameter. And if we want to get some number of days in the past to get our historical weather data, and we could say that there's some start date, which is equal to datetime dot UTC now minus the days. And for this, we need timespan dot from days And since this is nullable, we're going to say days.value, and we'll handle the case as some simple query validation here when days is null. So we can say if days is null, meaning that the user didn't provide that query parameter, we're going to return a bad request here. So we can say return results.badRequest. And let's think about this in terms of some very basic query validation or endpoint validation here. We don't want users to pull back the entire database, and we're not in a situation where we have a sort of web application and we're paginating data, at least not in this point in the application's lifetime. We're really needing to return back an entire page of data that corresponds to the zip code and that time range. This is going to be necessary because our weather report service needs to take all of that precipitation data from that period of time and build out a relevant weather report. And so we want to set some limits on this. If we were to call toList on this query, what EF is going to do is essentially execute that SQL query. And if we didn't have a where clause here, for instance, then we'd be doing a complete table scan. And remember, we're doing this in the context of an HTTP request. So that could be untenable for our particular use case here. We don't want to pull back potentially massive amounts of data. And so let's use some query validation here to sort of bound that request if we can. So let's say that please provide a days query parameter between 1 and let's say 30. So at maximum, a user will only ever be able to query up to 30 days in the past, which explicitly sets some limit on the query that we want to execute here. So for this, we have to say if days is equal to null, or days is less than 0, or days is greater than 30. Less than 1, apologies. Okay, so if that's the case, if a user doesn't provide a days query param, or it's some 0 or negative number or some number greater than 30, we're just going to cut it off there before we actually even construct a query for our database. So now we can say where the zip code matches and the precip.createdOn is before, or rather after, our start date. And just a typo here, this should be start date. Okay, and we can even make this asynchronous, just so you're aware. We can say async on the delegate here and toList async, and then await this. We just need to bring in Microsoft Identity Framework Core here, and we can return results.ok with results on our payload. And that should work really well for us, I think. Okay, and in order to connect to a database, we actually need to tell .NET how to get wired up to it via our new precip DbContext. So what I'm going to do here is we're going to call builder.services.add DbContext of type precip DbContext, which is the DbContext that we just created earlier. And as an argument here, we're going to have this function options that returns some options that we can provide here, including, for now, enabling sensitive data logging, enabling detailed errors, and then importantly in our case, to use npgSQL. Now we can get access to some configuration values here on builder. So we can say builder.configuration.get connection string, which is a helper method that pulls a connection string from a key appdb. However, our application is configured, and we're going to set the service lifetime here as transient. Okay, so what we want to do is that we want to set up this appdb connection string, so we can do that for now in our app settings file. So let's come into app settings, and then we're going to create a section here called connection strings, and then a key appdb. And here we need to provide our Postgres connection string. So the way this is going to work is it's going to look like this, and we'll walk through it. We have a host. For localhost, we'll be running this on localhost. Postgres default port is 5432. We'll have a username cloudweatherdev with a password cloudweatherdev for local, and the database will be called Cloud Weather Precipitation Dev. So remember, each of our microservices will have a separate database. They'll all be running on the same database host on localhost port 5432. So that's going to be very convenient for us. We need to provide this so that in our program.cs, when we call configuration.getConnectionString with appdb, it's a helper method to just find connection strings object here at the root level of the config, and then find a key appdb, which corresponds to this string here. Okay, so for this to work, we actually need Postgres running. And so the way that I like to do this when I'm starting out development locally is to actually set up Docker Compose to run a simple Postgres database locally. That way we can spin it up and down very quickly when we're developing. So what we'll do is we're in the root of our directory here, and I'm just going to create a new file called dockercompose.yaml. Feel free to use a text editor of your choice, of course, to do this. And I'm going to paste in a very simple Docker Compose file for us here. Okay, so what we have is a version 3 Docker Compose file, and we have a single service here called Cloud Weather Postgres. Now you'll see the image that I'm using here is a Debezium image of Postgres 13 running on Alpine. We have our, I'll talk about Debezium here in a moment. We've got a Postgres database called Cloud Weather Dev, and then a user and password that match the connection string that we just set up in our app settings.json file. For now, we can actually remove networks. This won't be necessary for us. So just to keep things as simple as possible, we have a single named volume Postgres data. This will actually allow our Postgres data to survive the lifetime of the container. That way we can run the container really only when we really want to, but we don't need to worry about losing data when we tear the container down unless we destroy this volume. So it's not really necessary here to use the Debezium image of Postgres. I just am using this because I have an instance locally. If you're curious about Debezium, it's very interesting. If you are using event-driven systems or systems which have derived data sources, like say you want an Elasticsearch index or some other search index to update sort of synchronously with your primary data store, if it's in Postgres, then Debezium provides a very nice way to stream Postgres events from the database to some external source, say as JSON, for instance. So we can actually sort of monitor the write-ahead logs in Postgres if we're doing logical logging in Postgres, and we can use Debezium to sort of view these changes as a stream of events. So this can be really useful for, again, situations where you have derived data sources, maybe in some type of cache or an Elasticsearch index or some other database. Outside of the scope of this particular video, but that's why I'm using Debezium here. I already have this locally, and I don't want to necessarily pull a different image for now. Okay, and now we can just run Docker Compose up. And if you don't have the Postgres image yet, it will pull, of course, and then the database will start. So I'm just going to run this in sort of attached mode, if you will, here, just to make sure that the database system is ready to accept connections. And that looks good, so I'm going to Control-C to stop it here, and then we'll run the same command, passing -D, to run this in detached mode. And then if we docker ps, we can see that the container is running, and that we're mapping port 5432 on the host to 5432 in the container, meaning we'll be able to connect to it from our host here for debugging purposes. Okay, so we have a database running. We have an entity framework DbContext set up with a table set up and a little bit of configuration. Now we can actually generate our first migration. And so the way to do this is we want to actually move into our Precipitation project folder. And we need to do one more thing here. We actually need to move app builder.build below builder.services.add DbContext. We want to add the DbContext before we actually build the application. And then back in our terminal, we want to make sure that we're in the Precipitation project directory. So we should see the cloudweather.precipitation csproj file here. We're going to run the command .NET ef migrations add, and I'm just going to call this initial migration. So what EF is going to do here now is it's going to create some migration files for us. And so in fact, if we head back into the project, we'll now see a migrations directory, and you'll see a migration that's timestamped with the timestamp prefix here. And then you can actually see the code that will be executed that runs against our Postgres database ultimately. So this will get converted into SQL, and then you can kind of see from a C# perspective what's happening here just by sort of inspecting this migration file. We can see we're creating a table called Precipitation that contains these columns, and we see the types here, UUID, numeric, and text. We scroll down, we also see a method down, which will drop the table precipitation. So on up, we create the table. If we go down, sort of reversing that migration, it will actually just drop the table. So in this way, we have a controlled way to move between states of schema. Okay, now all that's left to do is really execute that migration against the database. And for this, we run the command .NET-EF database update. Okay, and so that should have actually executed the schema change against our database, creating the Precipitation database. I'm going to open up pgAdmin now to see if we can connect to our local DB. Okay, so we're going to go ahead and unlock pgAdmin. And then if you don't have a server added yet for localhost, we can actually just go ahead and register a new server in one of our server groups here. Let's call this Cloud Weather Local. And for the connection string here, the host is localhost. The port is 5432. Postgres can be our maintenance database. And then the username here can be Cloud Weather Dev. And likewise, our password will be Cloud Weather Dev. So we'll go ahead and save this. We should be able to expand Cloud Weather Local now, and under databases we can expand this. And in fact, we see Cloud Weather Dev as the database for our Cloud Weather Dev user, but we also see Cloud Weather Precipitation Dev. And if we expand schemas, public, tables, we should see two tables here, a _EF migrations history table, which is used internally by Entity Framework to sort of track migrations over time, and then a precipitation table, which of course contains columns for ID created on amount inches, weather type, and zip code. Okay, so with that, we've now demonstrated that we can run migrations using EF6 for a single microservice. We should actually do the same for the temperature service here. So let's go ahead and set that up now. So I'm going to come back into Visual Studio. And perhaps before we do this, we'll do a commit. And we're going to say add data access to Precipitation service. Okay, so we're going to set up something very similar in our temperature service now. So we're going to go ahead and add a directory called data access. We're going to create two C# files here. One called temperature.cs and one called temp DbContext.cs. Then what I'm going to do is for temperature, we're going to have a GUID created on, and then we're going to track the high and low temperature in Fahrenheit here as decimals, and then a zip code string again. Now we can set up our temp DbContext. And just to avoid any type of confusion here in terms of like temporary, I'm going to call this actually temperature DbContext, which I think will be more clear. And we're going to have some very similar code in here. Just need to bring in Entity Framework Core. And we need to extend DbContext here. Okay, so we're going to snake case the temperature name, temperature table name here, which is just a single word temperature, so we lowercase it, and otherwise we have a single DB set here of type temperature. So we'll have a table called temperature in our temperature DbContext database. While we're working on data access generally across our software, I think I'd also like to set up the data access for the report microservice. So we'll go ahead and do the same here. This way we sort of get the data access piece taken care of. So data access, and the report is going to generate a weather report instance. So let's call this weather report. And the DbContext here will be called weather report DbContext. So we extend DbContext as before. And the DbContext implementation itself is something analogous. Let's call this weather reports, but something analogous to what we've seen before, of course. And the weather report object itself, or class itself, looks something like this. So again, we'll have a unique identifier in the form of a GUID created on. And now we're going to basically calculate the average low and high temperatures for some period of time, as well as the total amount of rainfall, the total amount of snow for a particular zip code. So that'll be all business logic that we really need to work out. But for now, this gives us a nice sort of setup in terms of data access for each of our other two microservices. So let's go ahead and run database migrations for each of these. So we can go up a directory here and then go into cloudweather.temperature, and then .NET-EF migrations add init. And here you'll note that we're throwing some errors. For one, we actually need to provide the DbContext for each of these classes. So I'm going to save everything here. And for the program.cs in temperature, we're going to open this up. And as you recall, we still have sort of the very minimal amount of code needed to run this application. We're going to look at the way we set it up in program.cs in the precipitation. We'll go ahead and copy this section out. We'll head back into program.cs in temperature and then post the same, except here we're using the temperature DbContext. And we'll bring in the correct namespace as well as pgSQL. We'll need to set up our connection string here as well. So let's go ahead and do that now. We'll open up app settings from precipitation. We'll grab the connection strings setting, and we'll open up app settings.json in temperature, and we'll add it here. And we're going to change the database name to temperature_dev. So cloud weather temperature dev. We use the same username and password for now to keep things simple. And now we'll head back into the program rather, and we're going to add the DbContext for our weather report service as well. So in program.cs, come here, and this will be weather report DbContext. So we'll bring in the appropriate namespace, use pgSQL, and then copy our app settings.json for this connection string for the weather report here, and we'll call this cloud weather report dev. Okay, with that, let's go ahead and make sure everything builds, and we're looking good. So let's head back into our terminal. We'll clear, and then we'll go ahead and try to run our first migration for the temperature service again. Okay, so we ran. Now we should be able to run .NET-EF database update again for our temperature service. And it looks like we're good, so we're going to go up a directory now into cloudweather.report. We'll run .NET-EF migrations add init for the initial migration for our cloud weather report, and then .NET-EF database update to generate our weather report database. Okay, so if we head back into pgSQL here, what I'm going to do is right-click on databases and just refresh, and now we should see 5 of them. So we see indeed our cloud weather report dev and cloud weather temperature dev in addition to cloud weather precipitation dev. And we can confirm that the tables are in there under schemas, public, tables, and we see a temperature table, and then in report we see a weather report table. Okay, so things are looking pretty good there. I think it's time to make a commit. I'm going to say add data access for remaining microservices, and we'll go ahead and push our changes here. Okay, with that set up, let's go take a look back at our program.cs in our precipitation service and kind of think about anything else that we might need here. Now we've mapped a GET request where we know that we have a way to get data from our database. We should also look at a way to make POST requests against our database. And as you may have guessed, the way to do that is by calling map_post. Now, what we want to be able to do is to essentially record new precipitation observations. And this might be handled in reality through some type of sensor, might be handled through some type of external API. It could be really anything, but really we need a way to ingest these observations from our perspective as a precipitation service. And so what we're going to do is we're going to expose a POST request endpoint to accept that data in a particular shape. And so what we'll do is we'll have at just the base observation endpoint here, we're going to create a function that writes new records, precipitation records, to our precipitation database. And so what we'll do is we'll accept a precipitation model, essentially a data model, as the as a payload on a POST request. And we also need our precip DbContext here. And the only thing that I'm going to do here is I'm going to say precip.toUniversalTime. And the only change I'm going to make inbound on the precip model is to say that precip.createdOn is equal to precip.createdOn.toUniversalTime. And then what we're going to do is await db. We can actually add async here, our precip record. And then in order for Entity Framework to actually persist our changes, we need to call save changes, or in our case, save changes async. Without this, if we just add to the collection, basically EF is sort of tracking a collection that might be theoretically modified over time in terms of our logic here. And so it's going to basically try to track all the changes to our database before essentially executing this. You can think of this as sort of wrapping all of this in a single database transaction that doesn't get committed until we call save changes async. Now over time, we want to really think very, very deeply and clearly about the interface of our API. So as the stewards of this microservice, we want to define a very clear and easy to use and stable API. So we want our API is our contract. It really represents our contract between us and anyone collaborating with us, our clients. So it may not actually be very prudent to define the type that we're accepting on a POST request here as being the same thing as a data model, which is our precipitation type, which is exactly what we're doing here. It's probably more prudent to create something like a resource model, something akin to, say, a Vue model in the case of data that we're sending out, if this were sort of a standard MVC web application. And that's because it should really be, we should really essentially hide the definition of how we store and represent data and not necessarily leak that abstraction out to our users in the form of, the contract with which we use to communicate with our users with. So as this application evolves, I would think about having some type of precipitation resource model, which may for now in many ways map one-to-one to our precipitation data model, but is not the same thing. And that allows us to change internally the types that we use to store data and separate the concerns from the DTO, the sort of data transfer objects that cross seam boundaries. And so that's just something that we might want to think about here. It's a trade-off that we're currently using the precipitation data model. And again, this may not be the right long-term decision. Okay, but this is enough to accept something of the shape of a precipitation data model via JSON on a POST request and save it to our database. We're going to do something very similar on the temperature service when we get to that point. In fact, let's open up temperature service and start thinking about its implementation in the program.cs file. So again, we're going to map a get and a post response here on two separate routes. I'm going to go ahead and close all tabs but this one. And in fact, the get request is going to look very analogous to the get request on the Precipitation service. So let's go ahead and grab this. And instead of a precip DbContext here, we have our temperature DbContext. And instead of precipitation, we have temperature. Here we need to bring in Microsoft.ASP.NET Core.MVC, which we can see now brought in here. And otherwise, the logic for retrieving records is identical to the logic for retrieving records of type precipitation. This time we're just saying, hey, give me temperature records for a particular zip code that go back in time some number of days. And to that end, in fact, the post request will be similar as well, except for the types. And again, we have the same sort of caveat that we're using the data model here for the in place of what would typically be a resource model. So something that we want to keep in mind here. For the sake of simplicity for the demo, I've just left this as the data model. But again, best practice here, I would say, would be to strongly consider separating a resource model from a data model. Okay, let's go ahead and build, and then if everything looks good, we'll push our changes. So I'll go up to the solution directory here and .NET build. And then add. And push. All right, the last service to really think about here in terms of microservices is our weather report service itself. So our weather report service is actually the most complex of all three microservices because it actually needs to receive a request from our user, and then it needs to actually make subsequent API requests out to two separate services, wait for that data to come back, sort of aggregate it into a weather report, and serialize that on a response to the original client. So for this, I'm going to actually create a directory for a service that actually handles this business logic, and we'll call this business logic, this particular directory. We're going to add a new class here. We're going to call this class Weather Report Aggregator. So we're going to also define an interface for this class called iWeatherReportAggregator. And I'm going to add an XML doc to this that says that this aggregates data from multiple external sources to build a weather report. And it's going to contain a single method that builds a weather report. And it's going to return a data model instance of weather report as the culmination of a task here. And essentially, it's going to also persist weather report data that's queried into its own Postgres database. So we could think about actually using the database that the weather report is managing as a sort of cache to cache requests for a particular weather report that gets constructed, so that if subsequent requests for that same weather report comes in, the Cloud Weather Report microservice doesn't actually need to go out and make HTTP requests. We could sort of shortcut that and prevent it from making duplicate round trips on subsequent HTTP requests for the same data by essentially treating its database as a cache to sort of just serve back that pre-calculated report. So that's something that we could definitely think about. So here we're going to bring in a few backing fields that we'll talk about. We're going to bring in an iHTTP client factory. We're going to use this to create instances of HTTP clients that can then make HTTP requests out to other microservices. We're going to inject a logger, and then we're going to create a type weather data config that we'll look at shortly here. This is just going to strongly type our configuration. And then finally, we'll bring in our weather report DbContext so we can interact with our own database. So here's a look at the constructor. And we need to actually put this constructor in the class, of course. And we're going to use the options pattern, finally making use of Microsoft.extensions.options here to basically map our strongly typed weather data config and inject it into this particular class. So let's go ahead and create this config now. In weather report, I'm going to add a new directory, new folder here called config. And inside of this directory, we're going to add that class here called weather data config. Now this configuration is just going to be used again to, in this case, configure the location, the endpoints with which it needs to communicate with the temperature service and the precipitation service. So remember that the weather report needs to actually make HTTP requests out to other services which could be hosted anywhere, and so we need a way to configure those values. So to that end, we're going to create 3 properties per collaborating microservice: a precip data protocol, so for instance HTTP or HTTPS, the host, the port, and then the same for the temperature service. So now we can bring in this namespace. So we bring in cloudweather.report.config, and we'll make our class extend our interface. Now with this, we can implement the interface using our IDE. We're going to make this async. And now what we need to do is essentially create a new HTTP client so that we can make HTTP requests. And so we can create a var HTTP client is equal to http.createClient. Then what we want is a way to fetch precipitation data and to fetch temperature data, provided some zip and then number of days to get that sort of time span for days in the past, to build that historical weather report. So you can imagine that we'd have some method called fetch precipitation data, and then we'd also have one to fetch temperature data. So we'll create those 2 methods here. We'll generate the methods. These can just be private methods. Now when we fetch temperature data, this can be an async method, which itself is going to return a list of temperature observations. And we're going to make these of type temperature model. Now we don't want to reference the other microservice, the temperature microservice in our report here. Again, that creates this dependency between the 2 projects. So we're going to create a models directory in weather report here. So we can go ahead and add a folder here called models. And in fact, we're going to create several models. We're going to create a new class here for temperature model. And we're going to create a class for precipitation model. And the only thing that our precipitation model actually needs here are the amount of inches of some particular weather type. So this will be sufficient data for our weather report to actually get built. So we're going to go ahead and bring in cloudweather.models namespace. And then for fetching precipitation, we are going to bring in a task list of precipitation models. So each of these 2 private methods receives the HTTP client that it can use to make requests out to those separate services, providing those services with the zip code and the number of days. So let's think about fetching temperature data. Well, this should be relatively straightforward. We do have get endpoints on the temperature service. And so we're going to need a way to build out that service endpoint, just a helper function here to build out wherever the temperature service is hosted. Then we're going to use the HTTP client to make an asynchronous GET request. And then we're going to wait on that response. So effectively, this is a synchronous call. We need to wait for that response back to actually handle that data. And then we're going to take the content from that HTTP response back, read it in from JSON, and essentially deserialize it into a temperature model type, a list of temperature models here. So our GET request on the temperature, if we take a look at the temperature microservice, as you recall, we're returning a list of results of type temperature. We're just going to basically deserialize that into the data that we need on a temperature model, which contains two properties that should map directly, temp high F and temp low F, from that temperature data model. And then essentially we want to return that temperature data as the return from this method, or we return a new list, an empty list of type temperature model. So let's go ahead and write the small helper method to build our temperature service endpoint. So we'll do this actually down at the bottom here. This will also be a private method, which is just pulling in from our config the protocol, host, and port, and returning the string interpolation of those with that endpoint observation, with the path parameter zip and the query parameter days. Okay, so that should be sufficient for fetching temperature data. Let's now look at fetching precipitation data. For this, we'll have a private method to build the precipitation service endpoint. There's a bit of duplication here. We could definitely sort of consolidate the endpoint building probably into a separate method and maybe even put that on a class itself. But for now, we are pulling the precip data protocol, host and port, and interpolating a string to make a GET request against our precipitation service. And so now let's populate our fetch precipitation data method. So here, pretty straightforward. We need to make sure that we bring in system.text.json to work with the JSON here. Property name case insensitive setting to true, and the naming policy to camel case. This is something that we can provide to, provide to our sort of reading from JSON async, this deserialization here, to get back a particular type of casing if we would like to set it like that. This is something that we could actually do as well on the temperature endpoint itself as well. So if we do this, and then pass it as the argument to read from JSON async. Okay, so now we are fetching both precipitation data as well as temperature data. Now let's come back up to our high-level public method here, which is building our weekly report. We now need to sort of parse out our precipitation data and our temperature data and essentially run a few calculations to build out our weather report. For one thing, for our precipitation data here, we want to be able to get the total amount of rain and the total amount of snow. So let's go ahead and create those functions now. So we're going to create these here. These can be true static functions, and again, a little bit of duplication, but we could worry about refactoring as a follow-up here. Basically, we're going to take our precip data and filter by snow, and round snow to 1 decimal point, and then get total rain and round rain to 1 decimal point, again filtering on weather type here. So we have our total snow and our total rain, and let's say we want to log that data out as well. We can do that very easily here using our logger. And then for our temperature data, we want the average high and average low. So we can go ahead and calculate that on the fly here using .average on the temperature data and selecting the high and low temperatures accordingly. Okay, and with that, we actually have enough data now to basically build out our weather report object. And I keep calling this weekly weather report. This is just weather report. Okay, and then although we're not explicitly doing anything with it yet, let's go ahead and save the result of any of those queries to our database for now. So we'll add this to the weekly weather report database, or weather report database. Yes, I would like to call this weather report. And then we'll save changes again. Then we'll just go ahead and return weather report here. And I'm going to add a to-do for us to come back here and say use cached weather reports instead of making round trips when possible. Okay, so we have this class which does some business logic for us in terms of collaborating with external microservices, aggregating data that it retrieves back from them, and then serializing it into this weather report object, saving it in our own database, and returning it to any client that we would like to use. And so the client for this particular class is indeed the program.cs file in our report project. So if we head in here, what we want to do is basically wire up that service and the HTTP client. So we're going to add HTTP client, which allows that to be injected into our service. We're going to wire up a transient instance of our weather report aggregator, so that will live for the lifetime of the method call effectively. And then we're going to also bring in our weather data config and map this to a new section in our configuration called weather data config. So let's go ahead and set that up now. We need to enter app settings.json and create this new section. I'm going to create this under connection strings here. And you'll notice that the protocols for now are HTTP and the hosts are local hosts because we're running everything locally for the time being before we deploy. And now we need to get those ports for temperature and precipitation. So if you remember precipitation, if we take a look at that project in the launch settings, on HTTP, it's running on port 4000. So we'll come back. And temperature, if we take a look, I believe was running on port 3000, but we can check properties, launch settings. That is indeed running on port 3000. Okay, so let's just go right ahead and wire up our GET request that we need in our weather report program.cs file. So under weather report, we'll open program.cs. And then after we have built our web application, let's map a GET request here. So we'll map GET /weather report /zip in curly braces. And as before, we have this delegate. In this case, taking a string zip code, a from query, optional int, or nullable int, days, need to bring in MVC, and our iWeather report aggregator, which will be injected here because we're mapping the weather report aggregator type using dependency injection. I'll call this weather ag, and then just to sort of make things a bit more readable here, we'll do a separate line for these two parameters. And here we will make this async and we'll await weatherag.buildWeeklyReport with the zip and the number of days. And in fact, I'm going to rename this, of course, to build report. So let's rename this to build report. And here we pass days.value. And here again, we can say if days is equal to null. We could do query validation at sort of the highest level here as well, or days is greater than 30, or days is less than 1. We could return results.badRequest with please provide a days query parameter with a value between 1 and 30. Otherwise, we return the report. And in fact, we can just say var report is equal to this. And then await results.OK with that report. Okay, so that should actually take care of the basic business logic for our weather report service. Now I'd really like to get some test data in place, and for that we're going to set up a data loader console application. So let's take a look at that now. So I'm going to close all of this, and before we do that we'll make a commit here. So we'll go ahead and add, and we're going to say add weather report, microservice logic, and we'll go ahead and push.